Hey, welcome back to Math with Patrick. Today is October 1st, and we're solving problem 274 from the Daily Epsilon calendar. And since we're back to the top of the month, the answer to today's problem should be 1, because it matches today's date, the 1st. So we have some problem here where y is equal to this sum right here. We have some notation with the choose function. We're squaring that value and then adding up a whole bunch of terms together. And once we learn what this value of y is, once we stick it here and divide it by another thing with kind of this choose function notation, we're supposed to get just the number 1 for x. So actually, if 1 is equal to 4050 choose 2025, or rather, if it's equal to that divided by y, I could just multiply both sides by y and say that y is equal to 4050 choose 2025. And this is also y as well. So the claim from today's problem is that this notation with the sum is equal to this notation right here. And I think first I want to talk about what that choose notation is all about with smaller numbers. So if we saw something that looked like this, I would say out loud as 5 choose 2. And this counts the number of ways we can choose 2 things from a group of 5 things. And I don't really care what order I choose it in. So like if I chose this one first, then this one second, that's really just the exact same thing as me choosing this one first and that one second. So we could just count up the number of ways, and whenever you're doing like counting problems, you should do it in like a methodical way. As in, like for this one, let's assume for starters that we are picking the first object. And let's just count the number of ways we can choose stuff given that we've already chosen the first object. And so we'll have one option here, or 2, or 3, or 4 separate options where we definitely have the first object. And now that we've exhausted all of those possibilities, we can think about, okay, what happens when we definitely have the second object? And I'm not going to count this one because I already counted it, right? Because I already counted it when I had this one, and they're the same group. So I only need to look to the right here. So the second and third object, or second and fourth, or second and fifth, that gives me 3 options. And then we can kind of see that we're just going to have 2 options for the next one, that one or that one. And then finally, we have just the last option, which is just take the last 2. So if I add up all of those, I get 4 plus 3 plus 2 plus 1, and that is equal to 10. And so there are 10 ways to choose 2 things from 5 objects. There is a formula for this as well, and the general formula is you'll take the factorial of the top number, and then you'll divide it by 2 factorials on the bottom. The first factorial is just going to be the factorial of that number 2. And then the other one is going to be the difference between these 2 numbers. Essentially, this 2 and this 3, or whatever numbers you have on the bottom, will always sum up to the number on top. So like if we had 10 choose 5, for example, the formula would look something like this, because the 5 and the 5 add up to that 10. If we have 10 choose 6, then one of these numbers would need to be a 6, and then the other one would have to be a 4. Interestingly, there is kind of symmetry here with the choose functions, because if you notice, this 4 is right there, and then if these both have to add up to 10, well, I mean, it's the exact same formula. And maybe this makes sense, because if you have 10 objects and you choose 4 of them, that's essentially the same thing as choosing which 6 not to pick. Or flipping around, if you choose 6 objects, you've essentially not chosen 4, and counting up the number of ways to choose 6 things or not choose 4 things out of 10 is just the same amount. The problem here with our problem today is that these numbers are really big. I don't want to think about 4,050 objects and the number of ways to choose 2,025 of them. One little hint that this problem is giving me, though, is usually when they choose the current year as a number in the problem, it doesn't really matter. So I actually want to study something else. I want to see if the sum from n equals 0 to any given number, not specifically 2025, I'm just going to call it capital N, the sum from 0 to capital N of, again, another capital N here, because that's the 2025, big N, choose little n squared. I'm really curious to see if this is actually equal to 2n, choose n. And with this, there are, I think, two ways I could prove this. The first way is with Pascal's triangle, actually. So with Pascal's triangle, we have just basically the set of rules where we start with a triangle of ones, and as we work our way down, the numbers below are going to be sums of the numbers above. So if I do 1 plus 1, I get 2. And then I'm kind of imagining that I have just invisible zeros everywhere else. And so that 0 plus a 1 will give me another 1. 1 plus that 0 gives me another 1. And so essentially we're just going to get 1s all the way down on those edges, and then more interesting numbers on the inside. So just kind of continuing Pascal's triangle, we got 2 3s there. This is 1 4 6 4 1, 1 5 10, 10 5 1. It's got this nice symmetry. The left side and the right side are the same. 1 6 15, 20 15 6 1. It alternates between like an even number of entries and an odd number of entries. Let's just do a few more. Why not? 1 7 21 35 35 21 7 1. And maybe I'll stop there. And my claim here is that there's a relationship between Pascal's triangle and these choose functions. And let's choose, how about this 10 right here? Because earlier I said that 10 was the same thing as 5 choose 2. And also, if you remember what I said about kind of the symmetry here, it should also be the same thing as 5 choose 3. And visually, looking down Pascal's triangle, this 10 represents that there's 10 different ways to start at the very, very top and reach this 10 under a certain set of rules. And the rules essentially are that I, starting at this 1, can either choose down and to the left or down and to the right. And based on these rules, I can kind of trace out different paths to get down to this 10. And my claim here is that that 10 represents the total number of ways I can start at the top and end up at that 10. Because if we kind of write out maybe with lefts and rights, my route will go left, left, right, right, right. So that kind of looks like this. Or maybe let's go right, right, left, right, left. So right, right, left, right, left. I have 5 letters there. And of those 5 letters, I am choosing 2 of them to be lefts, and that is this number right here. Or I am choosing 3 of them to be rights, and that's that number right there. So if we're counting the number of ways to approach this number, it is kind of thinking about it in terms of lefts and rights, but it is also a nice visual representation of that choose function that I did earlier. We don't need to think about having 5 objects and counting the number of ways to pick one of them or 2 of them. Instead, we can just kind of take a look at the entries in Pascal's triangle and not have to worry about counting them all up. So this row helps us with that kind of 5 object scenario. And so kind of working our way back up, we have 4, 3, 2, 1. And then this kind of in a silly way is our 0 object scenario. There's exactly one thing you can do with nothing, and that's just sit there. And then in our 1 object scenario, we do have exactly one option to either not take it or take it. And then it makes a bit more sense once we have kind of like 2 objects here, where if we want to choose none of them, we'll just sit there. If we want to choose one of the objects, well, we do have 2 options. And then if we want the whole pile, well, we could just grab it. And that's just one option there. And today I wanted to strike some kind of comparison between these 2 entries or these 2 sides of the equation by looking at entries or rows of Pascal's triangle. And let's just say for the sake of example, n is equal to 4 right now. Let's take a look at what the right side of the equation is saying. That's saying 8 choose 4. And so if I want to learn more about 8 choose 4, I guess I do need one more row of Pascal's triangle. So let's get that in there. That's going to be 1, 8, 28, 56, 70, 56, 28, 8, 1. And as we work our way in, so like this is the 8th row, and I want to consider this kind of like the 0th diagonal, because again, it kind of represents me choosing nothing. And then this is the 1st diagonal. This represents me choosing one of my 8 objects. So then we're going to have a 2, a 3, and then finally this number right here is my kind of, actually it's equal to 8 choose 4. It's this one right here. And apparently there are 70 ways to choose 4 objects from a total of 8. Okay, so that's what the right side says. It just says the number 70, and we can find it right here in Pascal's triangle. On the left side, it's a little bit more complicated. We have 4 choose n, and then we're going to sum up those ideas from n equals 0 to 4. And so I am looking now at the 4th row of Pascal's triangle. And just this notation right here would suggest that I add 1 and 4 and 6 and 4 and 1. But we do have that little square right there. So I do need to square those values. I need to square 1, I need to square 4, I need to square 6, and then the 4, and then the 1, before I then add them all up. That's going to get me 1 and 16 and 36, another 16 and a 1. 16 plus 16 is 32. 32 plus 36 is 68, and then tacking on those 2 ones does give me 70, which is the same number as right there. So this row number 4, does show that this equation is true, at least for this one example, although I do want some kind of convincing way to prove that it's equal for all the rows. So one kind of way I could maybe show it is like we could try to change the value of n to maybe n equals 5 and see what happens. Here I would need the 10th row of Pascal's triangle, but fortunately all we're really worried about is this number right here, so I don't need to compute all of the entries in Pascal's triangle. I just want like just enough to figure out what this number right here is. 56 plus 70 is 126, so that's another 126, and then so adding these together does give me 252. And then the idea is that if I square all of these values and then add up all of those, I should get 252. But let's go back and think about it in terms of like paths of left and right on Pascal's triangle. So we already know that, say, this 10 right here represents the number of ways we can go down Pascal's triangle to get to that number 10. And we could think about it in reverse, where if we take a look at this triangle down here and think about starting at that 252, this triangle that I just drew is perfectly symmetrical to the triangle that I drew above. There are going to be exactly 10 routes that we can take to reach that exact same number 10. So if we have 10 routes to get to this 10, and then 10 other routes from this 10 to get to this 252, then just by using kind of that fundamental counting principle, we have 10 times 10 number of routes that will go through this 10 and end up at this 252, or 100. And then also, if we take a look, say, at this 5 over here, there were 5 total routes to get over there, and then there's going to be 5 total routes to get back to this 252. And then maybe it might make sense to take a look at that 1 on that outside as well, because there's just one way I could get to this 1, and once I'm already here, there's only one way for me to get back to that 252. I have to choose all rights and then all lefts. And so it does make sense to do 1 times 1, which is just 1. There is one route. It's actually just the edge here and the edge there that gets back to that 252. And any route that goes through this 10 is going to be completely distinct from any other route that goes through, say, the other 10 or the other 5. So then it does make sense to add them all up to find the total number of routes to get to this 252. So it doesn't matter if n is 4 or n is 5 or 6 or 2025, this logic still applies. We're still going to be able to count the number of ways to get to this spot by looking halfway up Pascal's triangle and squaring each of those entries and then finally adding them all up. So that's the proof. There we go. N could be whatever we want, even 2025. These two things are equal to each other always. And then finally, that means in the special case of n being 2025, these two values are the same, and so the same value divided by itself will just give us 1. There is like one more way to kind of think about it, and we could think about it in like a combinatorics kind of way. This is like when you like count the number of ways to choose stuff. So it's kind of like what we're doing with Pascal's triangle, but here we could think about just like trying to choose people for a committee. Say we have 2n total people, and let's just assign half of these people, so n people over here, n people over here. Half of them are going to belong to group A, let's say. So we just have a whole bunch of people here who belong to group A, and then a whole bunch of people here who belong to group B. And it doesn't really matter how many group A people I have or how many group B people I have. I just want to pick a committee of n people. So one way to figure out how many ways can I choose n things from a total of 2n will just be to do 2n choose n. And this kind of mirrors what we were doing on this side of the equation. Now let's also think about like why I'm assigning A's and B's to everybody. We could also think, okay, there is the possibility that I happen to choose everyone from group B and no one from group A. So that would look like n choose 0 for group A, and then n choose n for group B, because I'm choosing all n people from group B here. Now, that's not the only way I could form a committee. I could also form a committee where I choose one person from group A, so I'm choosing 1 out of n things. And then I also have the option to choose n minus 1 things from group B. And the reason why I'm multiplying these values here is kind of the same reason why I was multiplying the 10 kind of here with the 10 over there. Just because if you're counting the number of ways to do thing A and thing B, you just multiply them together. It's kind of like if you have 5 shirts and 3 pants, you have 15 total outfits. And then I'm adding these things because this scenario right here is completely distinct from these ones. There's no chance that I have any overlap between having no people from group A and exactly one person from group A. And then I can keep just doing this, right? I could choose 2 people from group A and all but 2 people from group B. And if you remember from earlier, doing all but 2 people is just the same thing as just choosing 2 people. So each of these entries that I'm adding up are just the same thing. And then here I could write it as just that number squared because I'm multiplying it by itself. So n choose 0 squared plus n choose 1 squared plus n choose 2 squared. And I would just need to follow this kind of adding pattern finally until I'm at that place where I'm choosing everyone from group A and no one from group B. So this would kind of look like doing everyone from group A and then no one from group B. This kind of second row is me kind of showing that these two choose functions produce the same value. And then here I am writing it in that squared notation. And these two things should be equal to each other, right? This counts the number of ways that I can choose a committee of n people from 2n total. And then this kind of left method is a longer, convoluted way of just thinking through like, okay, what if I have 0 people in a 1 or 2 or 3 or 4 or 5 up to all of them? And each of these scenarios is going to be distinct, and adding them all together is going to perfectly capture all the total possibilities of choosing n people from a pile or a group of 2n of them. And this notation right here is just, I could use this in some notation again, n equals 0 to, well, I'm using this lowercase n, whoopsies. I guess all of these n's should be uppercase to kind of match that uppercase n that I have. Maybe I'll just change my variables for this example. I equals 0 to n of n choose I squared. This summation notation is concisely describing what's going on there. And then this is indeed equal to 2n choose n, based on this kind of idea of thinking about choosing committees. So maybe you want to think about it with Pascal's triangle. Maybe you want to think about it with combinatorics. Maybe there's a way to do this with induction. I don't want to do it. Either way, this equation is always true. And when n is equal to 2025, that satisfies our problem for today. Y and this value are going to be equal. And so finally, once we divide those values together, we get number 1. So that's my whole proof. I guess we're all done. Hope you enjoyed today's video, and I'll see you tomorrow. Bye.